Hello everyone, I am Nurettin. I participate this conference from Turkey that I want to talk about on k-generalized Fibonacci Diophantine Triples. That my title includes two different definitions. At first I want to give the definition of k-generalized Fibonacci numbers. Let k at least 2 and the k-generalized Fibonacci sequence whose terms satisfy the recurrence relation 1. With the initial conditions, the k minus times 0 and the last term is 1. If k is 2, then we obtain the well-known Fibonacci sequence. And if k is 3, and we obtain the Fibonacci sequences. The Diophantine Triples is defined a set of n-distinct positive integers a1, a2, and am such that ai, ag plus 1 is a square for all e less than or equal to I less than g less than or equal to m. That's we will interested in the special cases of this definition. That we will take m is 3. If we take the m is 3, we call it Diophantine triples. Namely, the set ABC is a Diophantine triple if AB plus 1 is square x, AC plus 1 is square y, BC plus 1 is square z. That if we give an example of this definition, that the set 1, 3, and 8 is a Diophantine triples since 1 times plus 1 is square 3, 1 times 8 plus 1 is square 3, and 3 times 8 plus 1 is square 5. If we generalize these sets, that we obtain the Fibonacci numbers. That's the set that f2 times n, f2 times n plus 2, 2 times n plus 4 is a Diophantine triples because the equation system of 4 satisfies. And there are lots of results about these topics. So I want to refer the web page of the Professor Andrei Zerler. That in 2008, that's Florian Luca and Laszlo Sala gave the different variation of this problem. That's, as you know, the right-hand side of the equation system, the square of the numbers, and they put, instead of the squares now of the numbers, they put the arbitrary Fibonacci numbers. Namely, they obtained the equation system AB plus 1 is fx, AC plus 1 is fy, BC plus 1 is fz. Here we put in a condition. That condition is a less than b less than z, and they are the positive integers. And they show that there is no solutions of the above equation system. Then after that, in 2009, that Luca and Saleh put here the right hand side of the equation, put the Luca numbers. They put the AB plus 1 Lx, AC plus 1 Ly, BC plus 1 is Lz. And they found only a solution. That the solution is 1, 2, and 3 is the only solution of the above system. If we put these numbers, that's 1, 2 plus 1 is 3 is the second Luca numbers. That's 1, 3 plus 1 is a 4, which is the third Luca numbers. That's 2, 3 plus 1 is 7, which is the fourth Luca numbers. Then after that, in 2012, we put right hand sides. We put on the right hand side, we put the balancing number. That balancing number is defined as second order linear recurrence with the coefficients 6 and minus 1, and the initial conditions are 0 and 1. Here the conditions is similar with the previous studies, that the conditions are a less than b less than c and positive integers, and we show that there is no solution of the equation system of 7. Then we generalize this problem that we put the right hand side, we put a second order linear recurrence with the coefficients of a and -1 and the initial conditions 0 and 1. That we show that there is no solution of the system for the a is at least 3 and a less than b less than c are positive integers. If we put a 6, we obtain the previous results. Then another perspective of these studies to enhance of order of these linear recurrence. That's to do this, Push, Atıl, Irmak, Luke, and Saleh show that AB plus 1 is Tx, AC plus 1 is T1, BC plus 1 is Tz have only finite Diophantine finite triples for a less than b less than c are positive integers. Here, Tx, Ty, and Tz are the members of the Fibonacci sequences. Then after them, Push, Luca, Hattel, and the Salai show that AB plus 1 is Akx, AC plus 1 is AKY, BC plus 1 is AKZ, have only finite triples for a less than b less than c are positive integers. If in this equation system, if we put k is 3, we obtain the previous results. So they generalize the previous results. That's my result is about the problem of the Fuchs, Hatzel, and the Saleh. That here they show that there are only finite Diophantine triples. To do this, they use the subspace theorem. And here I put an upper bound for the smallest of integers a, let's say 10 power 3. I put this bound and I show that there is no solutions of this equation system. To do this, I use the Math-View theorem. That Math-View theorem, as you know, and give the upper bound, give the lower bounds for the gamma, which is defined that gamma 1 power b1, gamma 2 power b2, and finally gamma t power bt minus 1. To do this, we must show that gamma is different of 0. By the equation system, we have the equation 30. And by the using of this formula and this formula which is given by the rest and 2, and if we put that this formula in the equation 13, we obtain the inequalities 14. That's here we obtain an inequality and the fk alpha is alpha minus 1 over 2 plus k plus 1 times alpha minus 2. And if you take that gamma 1 is fk alpha, gamma 2 is a squared, gamma 3 is alpha, and with the b1 is 1, b2 is minus 1, b3 is x plus y minus z minus 1. And after applying the Math-View theorem, we obtain the inequality 16. If we compare upper and the lower bounds, and we obtain the equation 17. That here we obtain an upper bound for x, which depends on the x, depends on k. From now on, we separate the two different cases. In the first case, we assume that k is at most 160. That first we assume x at most 70. By the result of the Fuchs, Hattel, Luca, and the Sala, which is giving the inequalities 18, we deduce that they at most 2,898. So when we use the Mathematica to find the solution, we don't find any solution. That from now on we assume that x at most 18. Since k is at most 160, we have that x is x less than this number. that this number is a very huge number. So our aim is to reduce this number to compute by to find the solution by using the mathematical. Let gamma is this number, and then we obtain the gamma is less than 6 over alpha power x minus 40. After applying two times LLR logarithm, here I don't give the details of these calculations because there are lots of calculations. We obtain the inequalities 2 and 1. And if we compare the inequalities 19 and the inequalities is 2 and 1, we obtain the x is between these is 18 and 33, and zx less than this number. If we use these bounds to find the solution, we don't have any solution here. That from now on, we will focus the second case. The second case, we assume that k is at least 160. For such k, we obtain the inequalities 23. Here, we use the key arguments of the Brau and Luca. Then we obtain that absolute value of these two numbers is less than this rational number. After dividing both sides with the 2 power z minus 3, we obtain the inequalities 23. That here, if we solve these inequalities, it is obvious that since x is that are integers, that this absolute value is greater than 1 over 3. Then when we compare 1 over 3 and the 11 over 2 power k over 2, then we obtain that 2 power k over 2 is less than 23, which gives a contradiction because we assume that k is at least 120. So the proof here is completed. Thank you for your attention again.